Continuing on with problem 10 here, 10 through 14, we have more retrosynthesis problems. On this one here, you see that the carbonyl has been removed here. We look at the product, it's not there anymore. And this new functional group is here. We have an amide here and we have another amide here, but the carbonyl has moved over to this one spot, and we have two extra carbons. We can look through our answer choices and see if we can eliminate things that do not have two carbons in them. Here, A, that's not correct. That only has one carbon in it. Now you always have to watch out. There's always cases where there's two equivalents, but this is not a scenario where we have two equivalents with adding an acetyl group there. B could work. We have to check that more later. C could work because we have two carbons here. Just looking at two carbons now. And then D is the trick. You see that two equivalents right there, and you're like, oh, I could add two carbons, but that's a trick. Don't get tricked. D is out because that only adds one equivalent of the methyl group to that. Okay, so two things happen here. When you do a retrosynthesis, if you see a transformation occurring, so here we have the oxygen here, and then we've removed an oxygen right there. That is a reduction, and reductions are where we add hydrogen. So we look at these two answer choices here. There's only one answer choice, this one right here, that adds a hydrogen, and that is a reducing agent. So this is our source of H, that's our reducing agent. So this one is wrong because it doesn't do the reduction part of it. Okay, and this could also watch out for problems where this could be out of place, meaning the sequence, the order is out of place. Watch out for synthesis problems of that nature. Okay, next one, number 11 here. Here we have the chlorine leaving group right here, and we see that we add in this nucleophile. So we're looking for a nucleophile here in this problem that's going to attack that. This leaves eventually. In this case, we only have a couple of different ones that's going to add this acetate nucleophile to it. One of them has acid in it, A. The next one here has the acetate molecule. And here, don't get confused with these sodiums or potassiums. Those are just counter ions. All they are to counterbalance the negative charge which is on the nucleophile. For our purposes, you can just scratch that out because those are never going to take a role in the reaction itself here, in organic chemistry at least. So there's a negative nucleophile, and that's what we needed in this reaction. We needed something with a negative charge here to attack the positive charge. In this one, this is kind of set up to lead you to believe this is some kind of Fischer esterification, but this is not a Fischer. This is the anhydride. And anhydrides are usually made with this manner here, adding the acetate to the acid chloride. Okay, next one here. A little bit of a fancy problem here, making this aldehyde here. And with this one, we have to count carbons just like we did before. We observe we have two different functional groups, chlorine versus aldehyde over here. Let me count this over here first. So that the chain is 8 carbons long. This chain over here is 7 carbons long. So we added an extra carbon to that one chain. Let's go to the answer choices here and notice that C contains no carbon. Right here, diol H does not contain a carbon that can be added to the molecule here. That's a source of the H's. That's a reducing agent. So what that means here that both C and D are out, and then we can go on to analyze A and B. A here, let's just start out. A adds a carbon, this one, Here you would have a SN2 attack, backside attack on the carbon there. And in the next two steps, we see our dibol H, which is our aldehyde making thing. So we can make an aldehyde of a cyanide here. So what we get here, we're going to convert this cyano group right here, and then once we add in, this is step 1, once we add in step 2 and 3, that will make the aldehyde like that. So that's the answer choice there. What's the matter here with B? We have this PCC, and that's going the opposite direction. PCC contains chromium, and it needs an alcohol to react. So that one is incorrect. Okay, 13 here. Most stable with these carboxylic acid derivatives usually means the most amount of resonance. So right here we have a nitrogen. Amides are typically the most stable out of all of them. That would also be the lowest frequency on the IR. Here we see this would be the least stable here with the chlorine because it has the least amount of resonance. An aldehyde here is also kind of unstable also, and that one there is because it does not have a donor group attached to it, and it's less hindered, less sterically hindered as well. Okay, going here to 14, last one of this page, we have the most reactive, which means the least stable. And that also means that we have the highest number, highest frequency in the IR. And it's going to be this anhydride here. A lot of times you can tell that by looking at the conjugate bases of whatever leaving group we have to see which one is the best leaving group. So here, let me do a little mini lecture on this here. If we have one of those leaving groups, we can have, say, chloride, and we look at the conjugate acid. I'm not sure what I said a minute ago, but conjugate acid, again, I'm tired. Benzene was out partying all night long. pK on that, can't even remember. My pK is pK -7 on that one. And let's see what else we have. An acetate, just referring to problem number 14 now. We have an acetate leaving group. Right here, if we look at this pK, that one's about 5 for acetate. We have a OR group here, which would be, what I'm doing is just adding a hydrogen here to the leaving group to compare its pK. I'm not going to write this over again. This one here is about 16. What else do we have? We have the equivalent of like this. I'm just going to write it like this. A negatively charged nitrogen here, which in the pKa tables, those vary depending on how many alkyl groups are attached. But for that one, it's usually above 30. We'll say 35 for this particular one, though that is not exact for that particular molecule. And then the last one here, a ketone, would be this one here, where we have methane. Oops. Methane here with the pKa of roughly 50. So you can see with this leaving group here, this goes from the most reactive, which is the best leaving group, to the least down here. Okay, and that's problem number 10 through 14.